Okay, so in this practical, physics specified practical, we are going to determine the half-life of a model radioactive source. Now, as you should have learnt in your lessons, that radioactive decay is a random process. The number of radioactive atoms present in a given sample will halve in a fixed time period, depending on the probability of decay for that particular radioisotope. Now, this is known as the half-life of the substance. Now, this experiment is a simulation in which the radioactive atoms are represented by small cubes, and the cubes are considered to be decayed when they land with a particular side facing upwards. So you can see we've shaded in one side black, and so whenever a cube is rolled and lands with a black facing up, we consider that cube to represent an atom that has decayed. Now, to do this experiment, you simply need 50 cubes in a tray. A margarine tub would be fine, and then a tray to roll them in to make it easier to collect them and count them. So, ensure you have 50 cubes, put them in a small tub, you shake the tub gently, and then you just simply throw them into the tray. Okay? You record the number of cubes that have landed with that black face upwards. So if I do that quickly, I've got 1, 2, 3, 4, 5, 6, 7. So remove those 7 cubes, make a record of that in my table, which I'll show you in a bit, and then you put the remaining cubes back into your small tub, hopefully without them going everywhere. Give them a little shake, and you throw them into the tray again, and again repeat the process by counting how many are showing the black facing up. 1, 2, 3, 4, 5, 6, 7, 8. Right, you need to stop after 10 throws, and that should give you enough data to calculate the half-life. Once you've collected your results in your group, you need to, in the third column, calculate the number of dice remaining. And this can be worked out by simply subtracting the number that decayed from the total number of cubes. So for example, if you start with 50 cubes, and in the first throw 7 faced black side up, the number remaining is now 43. Once you've got your group's results, instead of repeating it to get mean results, you can simply share the results in the class to get a much larger sample size. You can then plot a graph. So you're going to be plotting a graph, okay, showing the number of radioactive atoms remaining, i.e. the number of dice remaining on your x-axis, plotted against the number of rolls. Okay? And you're going to use this graph then to determine the half-life of the cubes. So here we have some results from a class set results where they had 8 groups of 50, so we had 400 dice in total, and the class average results are shown and plotted like this. Okay. Now the half-life can be determined from simply intercepting the gradient. So we start with the 400, and half of 400 of course is 200, so all I need to do then is trace or draw a line across the curve at this point. When I intercept the line of best fit, I simply go down to get the number of rolls that it took, and you can see I'm coming up here with 3.8 rolls, which is the half-life for the cubes. Now, one reason why the bigger sample size makes the data more repeatable is that it will smooth out any fluctuations in the data and reduces the effect of any anomalies, because you may have some anomalies that do not fit the line of best fit, but when you get the class results, you can see the data looks a lot smoother, and any anomalies, their effect is reduced.